Hello everyone, and today we are going to do some examples from section 4.4 linear independence. So the first problem we are going to consider is show that three vectors v1, v2, v3 are linearly dependent in R4, so four-dimensional space. Express v1 as a linear combination of v2 and v3. Remember that for vectors to be linearly dependent, one of them is supposed to be expressed as a linear combination of others. Here we have a clue that we want to express v1 as a linear combination of v2 and v3. So basically, guys, vectors are given. v1 is 1, 2, 3, 4. My favorite vector. v2 is 0, 1, 0, minus 1. And v3 is 1, 3, 3, 3. So what we'll need to do, we'll need to express v1 as a linear combination k1 v2 plus k2 v3. Well, I'm going to actually write down like vector v1 over here. And remember that because we are comparing x components to x components on the left and on the right, I'm just going to put like components as a column vector. Okay, so that's how we're supposed to kind of like solve it. So basically, guys, we are searching for k1 and k2. We're kind of guessing that they're linearly dependent, means that there is no, we do have a solution how to express one of the vectors through others. Well, here, guys, what I do see, I don't want to really solve this problem, but I do see that for the first component, I have 0 here and 1 here. Because I have 0 here and 1 here, I'm assuming that probably this coefficient is going to be equal to 1. Again, that's just guessing. You can solve it literally, just write down the system of equations. Consider 2 variables, 4 equations. If it has a solution, definitely like lots of them supposed to kind of disappear while we are doing Gaussian elimination, but I'm trying to guess. So now I'm going to look at the second component. Second component is 2, right? And I have 3 over here. Well, how about this one, negative 1? If a 3 minus 1 is 2. Let's check on the next component. 3. 3 minus 0 is 3. And 3 plus 1 is 4. So my guess checks. Actually, my k1 equals minus 1 and my k2 equals 1. Is it always going to work like that? Are you going to be always able to guess about solution? Of course not. It's just like you were a special case where it was easy to guess. But generally speaking, not always possible to guess about the solution. Okay, so these 3 vectors are linearly dependent because we can express v1 as a linear combination of v2 and v3. Let's move to the next problem. Problem 2. Somebody is giving us a set of 3 functions. 1, e to the power of x and x. And is asking use Wronskian to check for linear independence. I'm going to remind you what is Wronskian and how it's going to help us to check for linear independence. So Wronskian is built out of functions and their derivatives, and especially working in differential equations. And it's going to tell us whether the functions are linearly dependent or not without trying to kind of actually solve any equations. So how Wronskian is built? Wronskian is a function of x. It's a determinant which you combine out of functions, their first derivatives. We are lucky here. First derivatives are 0, e to the power of x, and 1. And in this case, because we have 3 functions, we're supposed to have 3 rows in this determinant. And the third row is going to be second derivative. and second derivative of 0 is 0, exponential function is still exponential function, and second derivative of 1 is 0. So let's calculate this determinant. Well, it looks like I'm going to use expansion by the first row, so I have 1 multiplied by determinant of e to the power of x1, e to the power of x0, and minus e to the power of x. Maybe it's not the fastest way, but just like, let's do it this way. E to the power of x, right, minus, and we are going to have a determinant of 0, 1, 0, 0, and the last one is plus x, and that's going to be the determinant of 0 e to the power of x, 0 e to the power of x, whatever is left over when you cross out. So minor of x. Well, this determinant is going to be equal to 0 because it has a column of 0. This determinant is also equal to 0. And for the last one, we are going to have 1 multiplied by e to the power of x multiplied by 0 minus 1 multiplied by e to the power of x. If we multiply everything, we are going to get minus e to the power of x. Remember that the condition for Wronskian for functions to be linearly independent is that it's not equal to 0 somewhere for x belonging from negative infinity to positive infinity. It does not mean that it cannot be equal somewhere. It's supposed to just have points where it's not equal 0 somewhere. In this case, we are lucky because e to the power of x actually just positive function. It's always greater than 0. So negative e to the power of x is going to be always less than 0. It's not never even equal to 0. Okay, so we are going to make a conclusion that the system is a set, I'm going to label it as S, is linearly independent. How would we decide that the set is linearly dependent? If your Wronskian is equal to 0 everywhere for every x, then the set is going to be linearly dependent. Okay, that's all for examples for section 4.4. And let's move to 4.5. Okay, guys, in section 4.5, we are going to talk about bases and the coordinates. And you probably already heard that a set is going to be called basis if it's a set of linearly independent vectors and it spans a space where it belongs to. In our case, let's consider a space of polynomial of degree less or equal than 5. I'm going to maybe kind of... So polynomials of degree less or equal than 5. So maximum degree is 5, but polynomial can have like other degrees of like power functions. Okay, and somebody gives us polynomial and they're asking what are going to be the coordinates of this polynomial if we consider a standard basis. Standard basis for polynomials of 5th degree or less is going to consist out of 1, x, x squared, x cubed, x to the power of 4, and x to the power of 5. And we had it in lecture, like why it's going to be standard basis. So how do we kind of find the coordinates? Well, basically, guys, remember that if you do have a basis, the coordinates are going to look next way. The coordinates are just the coefficients of linear combination when you represent your vector in that basis. For example, that's k1 vector 1 plus k2 vector 2, and like I don't know how many vectors you have, that in general kn vector n. So these are going to be basis vectors, and k's are going to be the coordinates k1, k2, kn, and we are searching actually for those k's. Well, what is interesting, guys, our basis vectors are exactly like 1, x, x squared, x cubed, x to the power of 4, and x to the power of 5. And they are already sitting in this polynomial. So this is the last one, this is the third one, this is the second one, and kind of, if you imagine multiplication by 1, that's going to be number 1. So if I want to express it or read these coordinates. I'm going to read the next set. I'm going to read that it's 3 multiplied by the first element of the basis. Then my next element here is 7 because x to the power of 1 is multiplied by 7. So I'm going to put comma 7. And then we don't have any square, so it's going to be 0. We have minus 5 by cube, so it's minus 5. And then we don't have any fourth power, 0, and fifth power is 1. So these are the coordinates. Okay, now let's try a different problem, like a different vector space. Imagine that we have a space of 2 by 2 matrices. For space of matrices 2 by 2, use standard basis. And find the coordinates for matrix of the matrix A equals -3, -2, 0, and 1. Well, what is actually standard basis for 2 by 2 matrices? Well, also we had it in lecture. Standard basis is going to be matrix 1, which is going to look like this: 1, 0, 0, 0. Matrix 2, which is going to be 0, 1, 0, 0. Matrix 3, which is going to be 0, 0, 1, 0. And matrix 4, which is going to be 0, 0, 0, 1. So actually standard basis has 1 in every like possible position. And that's how it was over here too, right? If you consider a polynomial of fifth degree, so we do have one vector is going to be like equal to 1, and the second one is 1 in the second position and the third position. So basically we kind of getting same. So now what are going to be the coordinates of matrix A? Well, it looks like if I multiply my first matrix 1, 0, 0, 0 by 3, I'm going to get this -3, and no other elements are going to be present. And then by -2, my second element, 0, 1, 0, 0. I'm going to label this is M1, and this is M2. And for M3, because there is nothing here, we have 0, it's going to be multiplied by 0, 0, 1, 0, M3. And the last one is going to be just 1, M4. Right, just because element here is 1. So now we are going to just look at the coefficients of each of these standard basis vectors and copy them, and they are going to be the coordinates. Okay, this is going to be the answer. Well, now we should probably consider slightly more complicated question. How to find the coordinates not in standard basis? What if the basis is not standard? Here we basically just look for like positions, right? How about that we have a set which is two-dimensional vectors, 2, -4, and 3, 8. And somebody is asking us, what are going to be the coordinates of vector W, 1, 1, in basis S? Well, basis S is not actually standard basis. We actually usually first check whether it's a basis or not. Remember, to make it a basis, it's supposed to be a set of linearly independent vectors. And we know how to kind of check for linear independence. We just kind of write down those vectors as columns, 2, -4, 3, 8, and find the determinant, right? Remember that if determinant of it's not equal to 0, they are linearly independent. If it equals to 0, means that you can eliminate one of the rows, means that we do have a solution for linear combination, right? So let's calculate the determinant. So 2 by 8 minus 4 by 3, which is going to be 16 plus 12, which is going to be what, 28, not equal to 0. So linearly independent. And there are two of them in R. 2 means that it's a basis. Usually, guys, if I'm not asking you to check whether it's basis or not, you don't have to. I'm doing this just to show you like how can other questions possibly look. Now, how do we find the coordinates? Well, we do have our vector W. I'm going to write it down as a column vector, and then I'm going to have K1, the first coordinate, and that's going to be my first basis vector, and K2, the second coordinate, and my second basis vector. Well, now I just need to kind of solve a system of equations, which is going to look like this. 2 minus 4, 3, 8, and 1, 1 here, right? This is just like unknowns, and if I figure them out, they're going to be my coordinates. Well, here, I don't know like how to do it the best way, but why don't we review a little bit Gaussian elimination here? So I'm going to divide my first row by 2 and get 1, 3 over 2, and 1 over 2, minus 4, 8, 1. Row number 1 equals row number 1 divided by 2. My next operation is going to row number 2 equals row number 2 plus 4 row number 1. And I'm going to get as a result 1, 3 over 2, 1 half. And if I take this row, multiply by 4 and add it, I'm going to get 0 here. 3 over 2 multiplied by 4 is 6. And if I add it to 8, I'm going to get a 14. And 1 over 2 multiplied by 4 is 2. And added to 1 is 3. Well, basically I finished my elimination, right? I can start doing back substitution. So I know that 14 K2 equals 3, from where K2 equals 3 over 14. I feel suspicious that I did a mistake somewhere because my numbers are not like making anything good, but well, that's probably there is no mistake. Okay, let's accept. Maybe they're wrong, but let's like just show how to do the rest. So now we need to find K1. So I have K1 from the first equation plus 3 over 2 K2 equals 1 half. Well, one more weird number. K1 equals 1 over 2 minus 9 over 28. Well, kind of weird, right? If I multiply by 14, I'm going to have 14 minus 9 over 28. And that's going to give me 5 over 28. Well, I'm getting very weird coordinates, but it doesn't mean that they're wrong. So K1 equals 5 over 28 and K2 equals 3 over 14. Well, those are going to be the coordinates of my vector W in basis S. Okay, well, I think that's all. For any other vectors, well, you can do basically same. So normally, guys, to find the coordinates, we'll need to find the coefficients in linear combination of the basis vectors to represent whatever vector you want to find the coefficients. So this is W vector, right? And this is your first basis vector, and this is your second basis vector. And we are searching for K1 and K2. They are going to be working as my answer. Okay, I think for sections 4.4 and 4.5, that's it. So I'll see you in class and probably we'll have more examples there.